Okay. All right, let's move on to the next slide here. Okay. I'm going to slide this up. Whoops, wrong thing, because there's 4 things on this thing, right? Photons passing through matter can undergo the following interactions, right? So this is talking about the photoelectric effect. When the photons go into that and into the atom, what can happen? Right, the photon is completely absorbed and the electron is ejected, right? That was the photoelectric effect. It hits the photon, passes all its energy onto the electron, kicks the electron out. That's the photoelectric effect. The second thing, the photon hits the electrons, but because the photon has less energy than that work function, it doesn't kick the electron out of the atom, but it does move it to a higher excited state. Number 3, the photon can scatter from an atom and lose some energy, so it just kind of bounces off. Right, but that's not 100% collision, effective collision, or 100%, what's the right word? I'm drawing a blank on the word I want. It's not an inelastic, 100% inelastic collision. Thank you. And then number 4, the photon can produce an electron-positron pair. So it breaks the electron up into electron and positron. An electron and all positron is a particle that has the same mass as an electron, but has a positive charge. All right, and I will be honest, as I've told you before, this is my least confident stuff. So I get the first 2, I'm very confident I get with the first 2. The 3rd and 4th, not quite as confident in my understanding of what's happening here. All right. So let's continue through and work our way through this together the best we can. All right, here we go. All right, this is the pair production idea, right? Number 4. Because the first 2, like I said, we did photoelectric effect. You can kind of visualize, I think you can visualize a photon not having enough energy, but enough to kick the electron to an excited state. This is the electron-positron pair production. Energy is conserved through the mass of the kinetic energy of the electron and the positron. There's opposite charges. The interaction must take place in the electromagnetic field of a nucleus, which can contribute momentum. Again, I apologize for my lack of understanding, but of this. It might. Okay, but I'm going to read through the example here, example 2-9 on page 765. We'll read through that and see if we can work out this concept together. All right, the one thing I do understand about this is during the collision, right, since it's producing an electron-positron pair, it's making a new electron, right? It's not kicking an electron that already exists out, it's producing an electron-positron. So if it's producing an electron, conservation of charge says it has to produce a positron, right? Since it started with no charge, it has to end with no charge. net. That's the only thing I really am very confident about, to be honest. Right, when it's making this pair. All right, so let's see if we can read through this example and work our way through this example together. It says, what is the minimum energy of a photon that can produce an electron-positron pair? And what is that photon's wavelength? Okay, here we go. Approach, the minimum photon energy equals the rest energy of two particles created based on Einstein's equation E equals mc squared. There's no energy since it's the minimum. There's no energy left over, so the particles produced will have zero kinetic energy. Okay. So the idea here is that the energy is mc squared, right? Equals mc squared. We've all heard of that equation, hopefully, right? That's probably the most famous formula in physics. Since we're doing an electron-positron pair, we're going to have two. The mass is going to be the mass of two electrons, right? Because, right, a pair of things. So the energy must be 2 times the mass of the mass, 9.1 times 10 to the, yes, 9 times 10 to the negative 31 kilograms. And C is 3 times 10 to the 8th meters per second squared. So the energy to make a electron-positron pair has to be whatever that is. 2 times 9 is 18 times 3 is 56, right? Slightly more than 56. Times 10 to the negative 31, 16, negative 15 joules of energy, right? Rounding, doing the math in my head. And then, so the wavelength of that photon must be, right, E equals HF, which would be HC over lambda. So energy equals H0, so wavelength is HC over E. And we could substitute and solve there. Right? Does that make sense? I'm still not entirely sure, so we can kind of work out the energy to make this part, but I'm still not sure why it happens. Reading the book, I still don't understand. Like I'm reading there's one paragraph that explains it, but it just doesn't say what causes this to happen. Photon disappears in the process of creating. In this example, the rest mass is pure energy. Photon cannot create. Right. So I apologize for my lack of understanding. So this is what happens. I don't know why. What would cause it to happen? I apologize, like I said, for my lack of understanding of this material. I can kind of work using the example, then work my way through solving problems and stuff, but I just don't understand the concept very well at all. All right, here we go. We ready to move on? Let's try and move on. Okay, I answered, or had you asked this question? You were asked this question in your homework that you just submitted, right? Is light a wave or a particle? And the answer is it's both, right? It's both, and it just depends on how you're looking at it, what your observations are when you're looking at the wave, right? If you're looking at the wave or you're looking at light and you're observing the double slit experiment or observation, it's clearly a wave. If you're looking at the photoelectric effect, then it's clearly a particle. So it's both. It just depends on the way you're observing the light and what you're observing out of it. Okay. Which most of you, actually all of you, said in one way or another in your homework when you answered that question in the homework. So let us continue. Right. If light is a wave, if a light wave can behave as a particle, then the particle must also behave like a wave. Excuse me. Right. So, right, wavelength is h over p, so it must be equal to h over mv. I don't remember what this example is, to be honest. I was a little lazy last night and didn't read ahead. I made up the slides and then I didn't read ahead and remind myself what would it determine the wavelength of an electron. Example 27-11, determine the wavelength of an electron that has been accelerated through a potential difference of 100 volts. The kinetic energy in classical physics is 1/2 mv squared. For the electron, because it's a wave and going at the speed of light, we need to do equals mc squared. So the energy is E equals mc squared, not using 1/2 mv squared, because of the speed it's moving. So an electron mc squared would be 0.1 or 0.511 mega electron volts. Right, if we did mc squared here in this problem. We then apply the conservation of energy. The kinetic energy acquired by the electron equals the loss of potential energy. After solving for V, we use this to find the wavelength. Okay. All right, again, this is, I'm coming to one of my shortfalls in this concept. And I apologize for that. All right, I'm going to move on to stuff that I do have some confidence in. And then we can come back and work our way through things together over the next few days if we need to. All right. Here we go. All right. Some just early models of the atom, plum pudding model. This is, you're never going to be asked about this, but right. But originally, just historically, someone thought the atom was this little like sphere that was this positive sphere that had electrons stuck in it randomly, right? Rutherford came along and said, nope, there's a nucleus that's positive with electrons that spin around it. And then after Rutherford was Bohr, who then came up with the idea of these electrons have specific quanta energy levels, right? Specific energy levels. They don't just randomly, they aren't just randomly spinning around the nucleus of the atom. Which brings us to, actually, do I have this in a, I'm going to skip one and go back for a second. Right? Bohr's atom, the electrons can only be in specific radius, only at specific ground or energy levels, right? So the electron can't exist in between the energy levels, right? I think we all have a decent understanding of that from chemistry, right? And this is an important concept because, I'm going to go back a step now, back a slide. I put this in a bad order of this idea, right? Radiation and the emission and absorption spectrum. When we look at a star, let's say we look at the sun. If you could actually break down the sun's visible light spectrum, if you actually look at it, what happens here is you can see in these little, hopefully you can see, little black lines, right? So yes, you get from Roy to Biv, but there are also certain little black lines in the spectrum that don't appear. So why don't they appear? Right? The reason they don't appear is because the atoms that are in the sun, the elements that are in the sun, when the wavelength, the light is leaving the sun, when they crash into the electrons of those atoms, primarily hydrogen, that amount, that wavelength actually gets absorbed by the hydrogen, right? And it kicks the electron to the next energy level. So this wavelength, whatever it may be, is not emitted by the sun. And this wavelength, whatever it may be, is not emitted by the sun because hydrogen absorbs that wavelength of energy. So when we are looking at this spectrum, little black lines are related to the energy it takes to take an electron and kick it one energy level, right, out of the hydrogen's nucleus. I'm going to make up a number, make up that wavelength does this, right? And this wavelength does that. And this wavelength does that and kicks it up 3 energy levels. So each of these wavelengths is a specific quantum of energy within there. So we can identify what the sun is made of, primarily hydrogen, by this absorption spectrum. And you can do that for all of the stars, right? You can do that for all of the stars. An emission spectrum is the exact opposite, right? That black body that's giving off wavelengths, that gives off, it emits light. The heat of a black body gives off wavelengths, does the exact opposite because it only emits wavelengths at specific amounts of energy. When that excited energy, something's hot, so the electron is at an excited energy level. When the electron goes the other direction and loses energy, in the process of losing energy, That energy has to go somewhere. And where does it go? It goes into emitting a wave. Goes into emitting a wave. This energy, it drops 2 energy levels. It goes into emitting a wave of a different wavelength. Right? So an absorption spectrum of or an emission spectrum are the exact opposites. For, say, for hydrogen, if you notice, there's my absorption of hydrogen from the sun. Here is my emission of hydrogen wave from that excited to a lower level. Okay? And this is essentially what radiation is. Right? This is essentially that radiation, the emission of energy. Okay, did I hit everything? I think so. What's the last slide I didn't hit? Oh, basically saying that those energy levels are waves, right? That the electron, as it goes around a given energy level, doesn't go around in a pure circle. It goes around in a wave, which is a standing wave. So, as it goes around the wave, and so on, at given different energy levels. Right? Did you do that in chemistry? The shapes of those things of each different energy level. I don't know if you do that or not in AP. Maybe you, right, but you don't go like within, right? You do the S and P and S and P. Yeah, right. That's right. That's basically this idea here. Okay. Again, I apologize for my lack of confidence and understanding. We're going to work our way through this the best we can. All right. As we go through this. All right. So I'm thinking tomorrow we'll just take our day and finish up this chapter questions and problems. Right. And we'll decide if we're ready to go over them on Monday and do the quiz on Tuesday, or if we need 2 days to finish the questions and then take the quiz on Wednesday before our Easter break on this chapter. Huh? Yeah, I would prefer to do it that way anyway, just because. All right, but we'll. I understand. All right, guys. Thank you for your understanding and your patience with me. I appreciate it. And I'll see you tomorrow.